Hi guys, here in this video we are analyzing TS set 2018 Chemical Sciences. Watch the video completely to get detailed conceptual analysis of each and every problem. Okay, right, just look at the first question. Identify the following. Look at the given two structures. We have given with meso and enantiomeric relationships of first and second structures. We need to pick the correct one. Okay, right. Now, in general, if we find a plane in organic molecule, okay, just listen carefully. If we find a plane in organic compound, then that molecule is optically active, and we can say it is chiral in nature. Okay, and that molecule always produces enantiomers. Okay, so just keep this point in our mind. Now, if organic molecule doesn't have any plane of symmetry in it, then we can say it is optically inactive and it is a chiral in nature. Okay, so based on this point, we can give the answer for the given problem. Yeah, just look at the first structure. Is there any plane of symmetry on it? So you can't find any plane of symmetry through the given molecule. That's why there is no plane of symmetry on the Fisher projection of the given structure. Okay, right. So plane of symmetry is not there. That's why it is optically active, and we can, as we said, it is chiral in nature and it has enantiomers. So the first structure is simply enantiomer. Just try to take a mirror plane here, and you can get CH3, CH3, OH, H, OH, and H. Just look at these two structures. They are mirror images to each other. Okay, and that's why we can say they are enantiomers. Okay, now just try to take RS nomenclature. So we need to find about chiral centers first on the given structure. So we know that whenever carbon center connected with four different groups on it, then we can say it is chiral. Okay, now just look at the first structure. Is there any chiral carbon? So we have two chiral carbons on it because four different groups are connected on those two carbons. Okay, right. Now, so just try to give RS notation on the first carbon. In RS nomenclature, we need to give the priorities for the groups first. So hydroxy group gets first priority, then the branch gets second priority, methyl group gets third priority, hydrogen gets a fourth priority. The priority order is clockwise direction, but the least priority atom, that is hydrogen, is on horizontal line of the Fisher projection. That's why we need to take opposite notation for the given priority order. Okay, so it is clockwise direction, so opposite notation is S notation. So the first chiral carbon, we have shown that it is S. Now just look at the second one. Here this is the second. Give the priority order. Hydroxy group first priority, branch second priority, methyl group third priority, hydrogen fourth priority. Priority order is clockwise direction, but least priority hydrogen is on horizontal line. That's why we need to take opposite notation as S. So on two chiral carbons, we have S and S configuration. Okay, in that case, its other enantiomer is having R and R notation. Okay, right, it is confirmed that the first one is simply enantiomer. Now just look at the second one. Is there any plane of symmetry on it? So you can check that there is a plane, okay, which is going through the carbon and in between the two carbons of the ring. In that case, so you can see these two, or the two halves are resembling each other. That's why it is having mirror plane on it. So whenever mirror plane is present, as we said, it is optically inactive, and we can say it is meso compound. Okay, so by this analysis we can give the option C as the correct answer, because first one is enantiomer and second one is meso structure. Okay, now try to take RS notation on it. So for the further confirmation, here we need to look for chiral carbons. Here we have chiral carbon, here we have chiral carbon. Just try to give notations, that means priority orders of the groups. So we have 1, and CH2 gets the branch of CH2 gets second priority, methyl group gets third priority. So order is anti-clockwise direction, and that's why it is yes. Now just look at the second carbon here, chiral carbon, that is, so here 1, 2 and 3. It is clockwise direction. As you see, it is anti-clockwise, and another carbon, chiral carbon, is clockwise. You can see they are opposing each other. So that's why the plane polarized light doesn't move right side or left side. So we can say it is meso compound. Okay, so it is clear. Now next question, the Gauche conformation of N-butane possesses. So first we need to look at the structure of here N-butane. We can take CH3, so CH3 like this. Okay, so I'm just taking cis form of it. Now in that case, just try to take Newman projections. It is the best way to find the relation here. So I'm just taking Newman projection as CH3, and just take the front carbon and the back carbon as here CH3, hydrogen and hydrogen. Okay, now just look at this Newman projection. We can say it is Gauche. Okay, so we can say Gauche butane here, and on Gauche butane just try to look for is there any plane of symmetry. You can't find any plane of symmetry here on it. Okay, that means a plane of symmetry is absent. At the same time, you cannot get any center of symmetry. Okay, right. Now is there any principal axis of symmetry? Yeah, you can get a principal axis of symmetry whenever axis goes through two carbons like this. Okay, so on 180 degrees rotation, it simply we can get there two methyl groups exchange their position, and these two hydrogens exchange their position, and these two hydrogens exchanges their position. In that case, C2 is possible here. Okay, as we said, if organic molecule doesn't contain any plane of symmetry and the center of symmetry, then it is chiral in nature. Okay, so simply the given Gauche conformation of N-butane is having C2 axis symmetry and it is chiral. So second option, that is B, is the correct answer for the given problem. Okay, right. And next question, among the following non-benzenoid aromatic compounds, which is pi rich? Okay, here we need to look for this point, and based on that we can give the answer. If you look at all these three, all these are non-benzenoid aromatic compounds because they are all fulfilling aromatic rules. Okay, they are following aromatic rules and 4n+2 pi electronic rules. Okay, right. But if you look at the second one, the delocalization of the double bond takes place with electron-rich carbene ion. That's why this is our correct answer. If you look at first time's third one, the delocalization of the double bond taking place through the carbocation, that is electron deficient center. So from that case, we can simply say that here second option is the correct answer for the given problem. Now just look at next question. Here, among the following the aromatic compounds is, so just look at the second one, that is naphthalene. It is fulfilling all the aromatic rules. So here we have 5 double bonds, pi electrons, so total 10 pi electrons are there. Delocalization is possible. Okay, so it is fulfilling 4n+2 pi electronic rule. So we can say it is aromatic in nature. If you look at the third one, here that means the here you can see the bridged oxygen is there, and which is making the planarity of the molecule. In that case, all these 5 pi bonds can delocalize on this planar structure, and it fulfills all the aromatic rules, so it is aromatic in nature. Whereas if you look at the first structure, so just look at here. In this first structure, you can see hydrogens, they just project like this, and in that case, here the steric repulsions are observed in between these two hydrogens whenever it is planar structure. Okay, so due to the steric repulsions, simply the planarity of this structure removed, and then due to the lack of planarity, it is not aromatic in nature. Okay, right. And next one, so from this we can simply say that second and third are aromatic compounds. Now next question, among the following compounds the formyl anion equivalent is? Okay, another very important question, and just look at it. First thing, we need to know about formyl anion structure. So here you can see C double bond OH and negative charge. So this is formyl anion. We need to look for formyl anion equivalents. First one we have given with 1,4 dithiene. So this is 1,4 dithiene. Okay, right. And then whenever we have hydrogen and here negative charge, it produces formaldehyde when in the further reactions. Okay, that means simply which is equivalent to formyl anion. Now just look at acetylene. Is it equivalent to formyl anion? Yes, it is also equivalent to formyl anion. So just take acetylene here, CH. So whenever we take methyl lithium, it produces C triple bond C negative charge. Okay, and whenever it reacting with, simply for example, if we take a ketone structure, then further reactions it produces acyl equivalent product. Okay, so acyl equivalent product here. So from that case we can say acetylene is also equivalent to formyl anion. Now just look at the next one, ethyl chloroformate. So just take try to draw its structure, C double bond O, ethyl chloroformate. So here we have ethyl group. Okay, so ethyl chloroformate, here oxygen should be there, ethoxy group. So this is ethyl chloroformate, and ethyl chloroformate can also equivalent to formyl anion. So whenever we apply CH2 CH3 here, okay, in that case just take apply alkyl lithium, here is the formation of negative charge. Okay, and in that case simply elimination of that acyl chloride takes place. In that case here elimination of this CH3 takes place to form CH3 C double bond OCl, and next one here we can get C double bond OH and negative charge. So here is also possibility of acyl anion. Okay, right. And next case acetone, we have CH3 C double bond O CH3. So just apply same. We have, whenever we apply base, here is a formation of negative charge, and here is a formation of enolate, and enolate can also act as a just like umpalan carbon ion, and which is also equivalent to synthetic equivalent to formyl anion. Okay, right. Next question. So here what is the answer? Simply all the given 4 options are correct for the given problem. Next question, addition of BH3. So addition of BH3 to carbon-carbon double bond is. So here first thing, just to take alkene here, C double bond C. For example, I am taking branched alkene or R prime. Here is for example R. So whenever we apply BH3 here, always boron will be present from the sterically, that means less steric crowding position. So here boron approaches from sterically less crowded position onto the alkene, and hydride approaches from the sterically more crowded carbon. So in that case you can see here is in the next step we can draw just like this, C R and R prime or, so here H and B. Okay, so from this what you have just getting, simply it is anti-Markovnikov's syn addition. Okay, so addition is also syn. Okay, they are from same side. So it is anti-Markovnikov addition and anti-Markovnikov syn addition. So your second option is the correct answer for the given problem. Okay, right. Thank you very much. And if you are interested, just visit chemmasters.online website to get best online courses to get the guaranteed success. Thank you very much.